Hello everyone, I'm Himanshu Vasnani from Department of Mechanical Engineering. I'm here to discuss a lecture on material science, subject code is ME207. We are doing unit number 1, lecture 6 in this series. Today's topics are hot and cold working of metals, recovery, recrystallization and healing. So today's objective will be to have a basic understanding of hot and cold working of materials, recovery, recrystallization and grain growth. And after the lecture, students will have learned the basics of hot and cold working of materials, recrystallization, and grain growth. Now, the students will have understood various parameters of hot and cold working of materials, recovery, crystallization, and grain. So, let me first give you a short glimpse of what actually is twinning. In addition to slip, plastic deformation in some metallic materials can occur by the deformation of mechanical twins or twinning. See what happens that when the deformation takes place along a plane, so it may lead to allow maybe due to slip system, slip deformation, or maybe due to twinning. In slip, what happens? There is a plane that is deformed from its position. Okay, so it will lead to a kind of a plastic deformation. Okay, then here any plane can chip which has a maximum density depends upon the material to material and conditions, working conditions upon which it is applied. But when we go for twinning also in this plastic deformation takes place. Okay, in some metallic material it can occur. But here there is a formation of mechanical twin or twinning. So we call this as deformation by twinning. Twin means same, two things same. So you can see the concept of a twin, that is a shear force can produce atomic displacement such that on one side of a plane, the twin boundary, atoms are located in mirror image position of atoms on the other side. Now, what happens there is atomic displacement, okay, on one side of the plane, and you can easily see that after the twin boundary you will see a mirror image of on the other side. I can show you this with the help of a diagram also, like here see, deformation of crystal by twinning. It is clearly shown that there is a perfect region on the left hand side, and in between there is a twisted band or distorted region, twin planes, whatever you want to say, and you will see a mirror image of the other side, on the right hand side. And by twinning takes place in this way, producing mirror-like images on both sides in between a twisted region. Okay, so here the deformation also takes place apart from just slipping. Slipping, the regions may or may not be same. The deformation region above and below, they may or may not be same. But here in twinning, normally these kind of examples do come in front, and so we call them as deformation by twinning. Uh, so twinning is the movement of atoms in the lattice resulting in a division of lattice into two parts which are symmetrical but differently oriented. Okay, means what happens that there is a division of lattice into two parts which is looking same symmetrical but differently oriented, one on the left, one on the right. Then the amount of movement on each plane in the twin region is proportional to its distance from the twinning plane, and therefore a mirror image is formed across the twin plane. That means that what happens in this, that the amount of movement of each plane in the twinned region is proportional to its distance from the twinning plane. Twinning plane is the twisted plane. Okay, and therefore a mirror image is formed across the. Okay, so here what happens that you get twin planes. Okay, now in twinning each atoms moves individually. That is a condition that you should know. So here in the diagram also you can see that you get a uh, twin plane on both the sides in between a twisted region, and you can see that every atom how is it positioned. Okay, easily you can easily locate, and you can see there is a twist in the twin band or distorted region. Okay, thus creating similar or twin region on the other side. Okay, this normally is a kind of deformation. It may be somewhere useful, it may not be useful, it depends upon the conditions. Then, if you think about like slipping, tuning almost takes us place in the special planes termed as tuning planes. Okay. And like that of a slip plane, tuning planes are also mostly fixed in FCC face-centered cubic structure. In lattice, triple one plane is the tuning plane. You can see in the diagram that what is the kind of a tuning plane creating similar twins on both the sides. In BCC, 112 is the tuning plane, and in HCP, 112 plane is the tuning plane. In figure, the tuning plane is triple 111 plane, and ML is the tuning region. See what happens that these structures, FCC, DCC, and SCP, the face centered cubic structure, body centered cubic structure, and FCP hexagonal closed cubic structure. These structures that is are thoroughly studied. So based upon the study and other structures, we have a data showing that okay, this twin planes existed at this point, at this point, at this point, at this lattice. So this can be determined. Okay, so we have data, and based on this experimental results have been shown in front of you, depicting the all the planes. Okay, uh, and the diagrams also. Then we topic fold working of materials or metals. See what happens that in the workshop or in the mechanical workshop, you can say there are various kinds of working is done. In them, the most common type is cold working and hot working. Various operations that are performed in the workshop that are also divided between hot working and cold working. So the concept behind this hot working of metals and cold working of metals, or hot working of materials or cold working of materials, needs to be discussed. Okay, in some way or the other, each process is helpful and each process has some positive and negative effects. So we should be aware of what is all about hot working and cold working of metals. So first of all, let me start with the cold working. The cold, the plastic deformation of a metal at a temperature below that at which it recrystallizes. Okay. Now, cold working produces an increase in strength with the attendant increase in ductility. Since the metal strain hardens, the advantages over hot working include a higher quality of material and lower temperature resistance. In cold working, you do not heat the workpiece. The workpiece is at its normal room temperature, and then you try to work upon it. The work can be used of some mechanical strength or with the help of a hammer or anything in order to obtain the desired shape. Okay, if you don't give heat to the material, it is worked at a room temperature only. So whenever you are working during cold working, it may lead to decrease in ductility of the material and increase in strength. Okay, the surface finish may or may not be good. The mechanical properties may change. Okay, the dimensional control, obviously, if you are hitting it with a hammer, the dimensional control will, you can say, get that disturbed. Although we will try to achieve a dimensional control, or we will try to achieve proper dimensions, but it may disturb since it is a cold working process. Moreover, some cracks may also appear on the surface due to high impact of the, you can say, tool, maybe hammer or what. So on this, the total deformation is accomplished in a series of steps in which the piece is successively fold worked a small amount and then processed annealed. Okay. Now, process annealed is a annealing process that is used study in the heat treatment. Basically, it involves temperature and allow it to cooling it. End of furnace. I will explain you in the coming units. So here, what we want to say that the when the workpiece is successfully cold work, then somehow it is given some annealing. But this process is quite expensive, and you can say it is time consuming and little inconvenient. Okay. Overall, the cold working could improve the strength, but this also lead to an expense of conductivity. It will affect it. Okay, cold working process will improve strength, increase in strength, but there's a decrease in conductivity. There's also there will be you can say at the expense of conductivity, it will be affected. Now, strain hardening. Strain hardening is you can say the phenomenon whereby a ductile metal becomes harder and stronger as it is plastically deformed. Okay. Sometimes it also called work hardening. See, you can say that strain hardening is normally the work is done at room temperature. At in the you can say it's kind of a cold working. In this, what happens that the ductile material, whatever work we're doing, it becomes harder and stronger because it is cold work. It is not hot work, it is plastically deformed. The shape that has been changed. See, there are two kinds of deformation you study: elastic deformation and plastic deformation. Elastic deformation means whenever you apply a force on a particular material and you remove the force or the effort, automatically the material will regain its original position, like a rubber band. You see that you apply a force, and after a certain time you remove the force, it will regain its original position. That is elastic deformation. Plastic deformation means you are taking the rubber band allow above a particular expansion, and that it will, and if you that leave it at that time, it will not regain its original position. That is plastic deformation. Okay. So in plastic deformation, the shape that has been changed during the working, that cannot be regained again. Oh, sorry, that is permanent. The initial shape is not permanent. So here in strain hardening, what happens whenever you are working on a ductile material, you are doing cold working on the ductile metal, it becomes harder and stronger as it is plastically deformed. Okay, then automatically its ductility will get affected, as you know. Why? Because the temperature at which deformation takes place is cold relative to the absolute melting temperature of the metal. Okay, why? Because the temperature at which the deformation is taking place is cold. Okay, related to the absolute melting temperature of the metal at is cold. Now here this there is a formula given A naught minus AD upon A naught. So here you can see that A naught is the original area of cross section that has experienced deformation, and AD is the area of the deformation. So you can find out that how much percentage of cold work has been done on this. You can say that most metal strain hardens at room temperature. If it is sometimes convenient to express that most metals they normally, if you want to do strain hardening at room temperature, it will work, no worry. But it is sometimes convenient to express the degree of plastic deformation as perfect as percent cold work rather than as a strain. Okay, then they're saying that the degree of plastic deformation that is done during strain hardening is usually given as percent cold work rather than strain, because it is like a code working process. Okay, you are working on a workpiece, you are improving its strength, it's becoming harder, and it is getting plastically deformed. You're also doing it at the room temperature only, so it is a kind of a cold work. So you can say that it can be expressed as a degree of plastic deformation as percent cold work rather than as a strain. So here they have given the formula: percentage cold work is equal to A naught minus AD upon A naught into 100. It will give you the percentage cold work. A naught is A original area of cross section. AD is the area after deformation. A naught was before deformation. So this is how we got strain happen. Then we go to the hot working. See, this is also a process that is being used in the you can say workshop, and it is more commonly used. You have listened about various processes like extrusion or you can say forging. There are various processes that have been done, tube drawing. Uh, so these all processes they are done in the workshops and can be termed under hot working. So when metals are worked above recrystallization temperature, that is zero point 0.7 temperature approximately, they recrystallize while being deformed and they remain soft. What happens that you can say that the metal or the workpiece, sorry, if you heat it at a particular temperature, they are not melted, they are getting softened. Okay, melted is different thing, with changing of state. But here they are softened, and if that moment you try to, you can say, change their shape or deform them, then they recrystallize while they deform also. Okay, now metal billets are stressed and given massive deformation. This process is called as hot working. Okay. Then during this process, the metal is in a plastic state and it readily takes the desired shape. I repeat once again. During this process, the metal is in a plastic state. Okay, once the changes is done, is done. It will not regain its original position. And it readily takes the desired shape. That is a plastic deformation procedure. Now the cold working process is carried out below the recrystallization temperature. This hot working process is carried out at a above recrystallization temperature. We will discuss this the term recrystallization temperature in the coming slides. So you can just simply understand that cold working without getting heated, it works below recrystallization temperature, and hot working, as the name says, some heat is given, so it works above the recrystallization range or temperature. Uh, Recrystallization temperature, right? So usually hot working processes are at given a compressor stress, example in rolling, forging or extrusion that I just told you, these kind of processes that are used for this. Now the speed of hot working operation at a given temperature can be calculated by considering the amount of time required for recrystallization. The speed of hot working operation at a given temperature can be calculated by considering the amount of time required for recrystallization. Okay, I'm getting the point. I explain you once again. What happened that you are doing a hot working operation at a particular temperature. Now what happens that whenever you go for deformation, this deformation will lead to some recrystallization. Okay, the crystals arrange themselves in a better way to get the desired shape. Right. Now here what happens that uh, you can say uh, before the initial stage and after the deformation, okay, then how fast the hot working process will work, it depends upon the time required for recrystallization. Okay, so that is the speed of the hot working operation. So the operation has to be performed rapidly at higher temperature, obviously because it is a hot working process. The upper limit of hot working process is the temperature at which the metal begins to melt. That is the upper limit, but we don't have to melt the temperature, melt the workpiece. We have to make it soft, and usually it is about 40 degrees below the melting point of the material. This is just you can say an idea that 40 degrees below the melting point of the material you have to work. Okay, that is you can say the operational temperature of hot working of materials. Okay, because you don't have to melt it, you just have to make it soft and deform it with proper recrystallization. Because it is happening above recrystallization temperature. Now, in comparison to metals, alloys are more difficult to work. Okay, in hot working hardening, due to deformation and softening, due to annealing simultaneously. Obviously, these things matter a lot. These work. Then most hot working operations are done in several stages or passes. And the temperature in intermediate pass is kept well above the minimum hot working temperature, so the energy is deforming metal will be saved. See, this is simple thing that whenever you are doing a work, you will pass through several stages. So they say that in the intermediate stage, they keep the temperature relatively well, so that the proper, you can say the temperature is provided, and the deforming takes place very easily, and the process get completed in proper time with proper speed. Yeah. The working temperature in last pass, the working temperature in last pass is just above the minimum hot working temperature. It's just enough to ensure that grain growth during cooling is negligible. Okay. I'll explain you this grain growth in the coming slides. To have finally the fine grain size structure, the working temperature is in the last pass is lower. They lower the temperature in the last pass. Okay. Okay, this is storage temperature usually above the minimum recrystallization temperature. See, during the process, they maintain something about above crystallization temperature. That's some temperature. In the intermediate, they supply the completeness of the this temperature, and in the last, they try to lower in the last pass. Okay, because they want the work to be finished in a better way for achieving proper deformation. The purpose is to deform the material in a better way and to attain good properties. Purpose is just simply that, to attain the new shape. Now the amount of deformation in the last pass has to be large for the decrystallization grain size. Okay, high rates of deformation are undesirable as they inherit the characteristics of the cold working process. We cannot deform too much or too fast. They are undesirable. Okay, because somehow cold working properties may get some, like the surface may break or surface may not be proper, or some properties may differ. Okay, like strength may differ and ductility may differ. So these are things that will affect it. The common hot working processes are rolling and hot drawing and hot spinning, hot extruding, forging, welding, hot piercing. This I know you all know this kind of processes. Like you can say forging is heating the workpiece to a particular temperature and then applying force on it to get the amount required deformation. Like swords and other fighting materials were prepared by the people in the king's times. And welding is like joining two parts with the help of a particular metal with the help of fusion process. This is welding. Okay, so there are different extrusion is there. Okay, so this is simple hot working processes that have been studied for now. The important advantage of hot working processes are like this. It has some important advantages, some disadvantages also. So we'll discuss both of them. Like power required is less. Okay, power required is less, and there is less danger of cracking the metal. Now, due to the pressing together of cavities, cracks, and low holes by the pressure used in the hot working, porosity in the metal eliminated to a great extent, right? Okay, then grain refinement is possible as coarse grain of casting are broken up and refined also smaller recrystalline grain. This is the grain refinement is happening there. An intermediate annealing is eliminated, impurities are squeezed into fibers and distributed into the mass. throughout the mass. Sorry. Here, this is also helpful that intermediate annealing is eliminated. Okay. Then desired directional properties are obtained from the fiber structure due to directional flow obtained in the hot working. Right. They get a desirable directional properties obtained from the fiber structure. Then relatively large deformation is possible without producing fracture as compared to cold working. Yes, they can go for large deformations, plastic deformations, but they there is a that they will not produce a fracture. Whereas cold working, a fracture may occur, means breakdown of the workpiece. Mechanical properties like strength, ductility, and impact resistance are also obtained due to gain refinement. Various mechanical properties because there is crystallization, so automatically they are the gain is getting refined, so they are improved due to gain refinement. Hot working is economical and also rapid for forming all commercial methods. Okay. Now disadvantages, sorry, limitations also. At high temperatures, due to rapid oxidation and scaling of the surface of the metal, the poor surface finish of the metal output is obtained. Then maintenance of temperature is usually difficult, particularly for light sections of thin sheets and fine fibers cool very rapidly. They cannot maintain the hot working range. So there is this difference in maintenance of temperature for thin section and thick sections. Due to poor surface texture, it is difficult to maintain close dimension tolerance, which is possible at all. The metals, because there is a high temperature, it is difficult. So the metals which are deficient in plasticity cannot be hot worked. These are termed as metals known as hot shot. Okay, hot working is usually performed in air, and hence lot of metal is lost in oxidation. Obviously, the hot working process is costly because the equipment used to withstand high temperature operations like rolling, forging, they are very costly. Right. So moreover, the life of the tools used in this process is relatively reduced due to their use at high temperature. See, this is a major equipment that that's why the equipments are also costly, and that is the process is also costly for them because everything requires some maintenance, and maintenance requires some cost. A difference between hot working and cold working of metals. A small slides for having some differences. Like in cold working, it is done at a temperature below the recrystallization, whereas hot working is done at a temperature above recrystallization temperature. Second, it is done below recrystallization temperature, so it is accompanied by strain hardening. And hot working is said hardening due to plastic deformation is completely eliminated. Then cold working decreases mechanical properties of metals like elongation, reduction of area, impact value, and hot working it increases mechanical properties. Then cold working crystallization does not take place in hot working crystallization takes place. Then in the cold working material is not uniform after this working. In hot working the material is uniform throughout. Then in the cold working there is more risk of cracks. In the hot working there is less risk of cracks. In the cold working increases ultimate tensile strength, yield points, hardness, fatigue strength, but decreases resistance to corrosion. Okay, ultimate tensile strength, yield, hardness, and fatigue strength, but it decreases fatigue strength, but decreases resistance to corrosion. There is hot working, ultimate tensile strength, yield strength, while corrosion resistance are unaffected. Now in cold working, internal and external stresses are produced. Obviously, you are not heating it, so obviously stresses will. And in hot working, internal and stress in residual stress are not produced. Cold working require more energy for plastic deformation. That is okay because it is not soft. It is still hard at room temperature, so it require more energy. Then hot working it requires less energy for plastic deformation because at high temperature metal become more ductile and soft, not melted, only softened. Okay, it's not melted, it's softened. Then cold working, more stress is required. Hot working, less work, less stress is required. Then cold working, it does not require tickling because No oxidation takes place. Then they say that heavy oxidation occurs during hot working, so cooking is required to remove oxides. Then cold working embrittlement does not occur in cold working due to no reaction with oxygen at low temperature. In hot working, there are chances of embrittlement oxygen in the hot working. Hence, metal working is done at inert atmosphere for reactive. So in the bottom, you can see some diagrams when it's having cold working, other is having hot working. Okay, you can see in the diagram what is the metal area, how are the rollers working, what is the water cooling in hot working. You can see very easily how the work is done. Now the terms come recovery. This term recovery implies all changes in the fine structure. This term implies all changes in the fine structure and properties of a metal, which involves no changes in the microstructure of the deformed metal, that is recovery, does not change the size and shape of grain. There is no change in the size and shape when doing recovery. The microstructure of the required metal doesn't change. Now, during recovery, some of the stored internal strain energy is relieved by virtue of dislocation motion as a result of enhanced atomic diffusion at elevated temperature. Okay, now this is what the work is done. There is some reduction in the number of diffusions configuration are produced having low strain energy. Also, the physical properties such as electrical and thermal conductivity and the like are recovered to their pre-worked states. So you can understand that if you go for recovery, there is some reduction in the number of dislocations and dislocation configurations are produced having low strain energies. Okay. Now recovery is further divided into two stages. One is strain relief recapitalization and second is polygonization. Okay. Now the first one takes place during heating of deformed metals, whereas polygonization can develop only under okay. Polygonization can develop only under appropriate conditions, whereas if you go with the strain relief recrystallization, it takes place during heating of deformed metals. Okay. Now, strain relief recrystallization we state at which the number of okay or from the lattice mainly vacancies diminishes and in a number of metals such as aluminium and iron strain relief crystallization also include dislocation which is accompanied with interaction of unlike signed dislocation and results in a noticeable decrease of dislocation density. Okay, now here what happens that strain relief crystallization of a cold deformed metal is the stage at which the number of defect points, mainly vacancies, diminishes. It diminishes. Okay. A number of metals such as aluminium and iron and strain relief crystallization also includes dislocation climb which is accompanied by interlinking of unlike signed dislocations and this results in a noticeable decrease of dislocation density. Okay. Now redistribution of dislocations can involve a release of residual stresses. As strain relief crystallization decreases the electric resistance and increases the density of a metal. The electrical resistance is decreased and the density is increased. When we talk about strain relief recrystallization. In general case, the hardness and the strength decrease at most by 10 to 15% from the initial value, and the ductility accordingly increases. Okay, so in this way, high resistance to corrosion cracking is there within the material. Okay, so this is a general system of recovery. Then you'll go with the polymerization. Polymerization that was strain relief crystallization. This is polymerization. Pollination is a kind of recovery involving the formation of new low angle boundaries within each grain. It is formation of new low angle boundaries within each grain, and these boundaries can form by slip and climb of dislocations. As a result, a grain is divided into subgrains or polygons which are free of dislocation. Okay, these are formed by dislocations like slip and climb of dislocations. So a grain is divided into subgrains or polygons which are free of dislocations. In commercial purity metals and solid solution alloys, polymerization is observed only after slight deformation and not in all metals. Okay. For example, this process only you can say rarely develops in copper and copper alloys and is well pronounced in aluminium or iron or molybdenum and alloys of these metals. Okay, you can see that only they are rarely develops in copper and copper alloys and well pronounced in aluminum, iron, molybdenum, and alloys of these metals. The polymerization of a cold deformed metal usually results in decrease of hardness and strength. This is somewhere interesting that of a cold deformed material it decreases in hardness and strength. So it is a matter of you can say a, a block-like structure appearing on polymerization can is quite stable and is retained in the metal almost up to the melting point. After deformation of a block-like structure, crystallization cannot take place. This is a simple diagram showing the strain hardened metal prior to polymerization. The A is you can say obtained prior to pollination, and after pollination you can get the B part, that is you can see how are these are arranged in B part and how is arranged in A part. So recrystallization. Now recrystallization is also important in term when you talk about such kind of things recovery and all. So I'll go with the faster with that. So recrystallization is the formation of new set of strain-free and equi-axed grains that is having approximately equal dimensions in all dimensions. Okay, what is recrystallization? It is a formation of recrystallization. What is this? It is recrystallization is the formation of new set of strain-free and equiaxed grains that is having dimensions in equal all directions. So that have low dislocation densities and characteristics of a cold worked condition. This is understood as the nucleation and growth of new grains with a small number of structural defects. Okay, the reflection results in the formation of new, uh, often EQX crystals. Okay, EQX means that having equal dimension in all directions. Now, the main driving force is to produce this new grain structure, and is the to produce, is this the difference between the new small nuclei and grow until they are completely consumed the parent material. And this process involves short range diffusion. Now, something more about recrystallization. That recrystallization of a cold work metal may be used to refine the grain structure. It will somehow happen. Okay. Moreover, during recrystallization, the mechanical properties that were changed due to cold working are restored to their pre-cold work values, obviously. This means that the metal becomes softer, weaker, yet more ductile. Just like recrystallization is plastically deformed metals that can take place only when the degree of formation has exceeded a critical value that is called as critical degree of deformation. Then only plastic deformation. Okay. Then with the degree of deformation is less than the critical value, nucleation of new grains during heating is impossible. Okay, the degree so nucleation of new grains is impossible. The critical degree of formation is not high, that is 2 to 8%. It is close to 2% for aluminum and 5% for iron and okay. Now recrystallization also is a process, the extent of which depends on both time and temperature. And recrystallization is also characterized by station definitely at recrystallization temperature Treg, which is the lowest temperature of heating at which the nucleation of new grains is possible. Okay, so this is also characterized by that also. So the recrystallization temperature of a metal constitutes a certain fraction of its melting point temperature. So here you can see that recrystallized temperature T rack is equals to A times of the melting point temperature. The coefficient of A depends on the purity of metal and the degree of plastic deformation. Okay, here this is given some kind of a risk that for brass alloy it is about 450 degrees centigrade. For commercial pure material it is 0.3 to 4.04% and decrease with increasing degree of deformation. Okay, now reducing the concentration of impurities can diminish the coefficient A to 0.1 to 0.2%. For solid solutions, sorry, the coefficient A to 0.1 to 0.2. For solid solutions, A is equal to 0.5 to 0.6 and can reach 0.7 to 0.8 on dissolution of high melting metals. For aluminum, copper, and commercially pure iron, the lowest temperature of recrystallization is equal to 100 degrees centigrade or 270 degrees centigrade and 450 degrees centigrade respectively. So increasing the percentage of cold work enhances the rate of crystallization with the result that temperature of recrystallization is lower and approaches a constant or limiting value at high deformation. It's a simple, you can say, diagram or you can say diagram showing all the temperatures, varying temperatures and the grain size and the tensile strength on the left hand side. You can see that new grains where they are formed and how the recovery takes place in the starting the crystallization and then the grain growth takes place. Okay, and the grain size is shown in millimeters. Between there is cold worked and recovered grains that is happening. Okay, and how it directly affected percentage in percentage elongation. The temperature here is given in somewhere different. In the bottom it is given degree centigrade, it is upper given degree Fahrenheit. So whatever you want to, so you can see. And the influence of annealing temperature on the crystal tensile strength and activity of brass alloy. You can say that the grain size as a function of annealing temperature is also shown here. What we have already shown. Then grain structures during recrystallization and greenhouse stages are also shown in this diagram. You can see the three different stages. Okay, now the green group. I will be a bit faster with that. I have to complete the lecture. So during recrystallization, the nucleation of new grains occur in the portion of the highest dislocation density. Okay, you usually get boundaries of deformed grain. The greater the plastic deformation, the more recrystallization centers appear in a metal. These centers are essentially some macroscopic regions with the least quantity of point and linear defects in the structure. You can see that here after certain times, sorry, these regions appear due to redistribution and partial annihilation of dislocation. And in this process, a low angle boundary appears between recrystallization center and deformed matrix. So after a certain time, deformed matrix, okay. After a certain time, centers of new grains increase in size due to passage of atoms of the deformed surroundings to a more perfect lattice. The high angle boundaries of new grains then move into the depth of strain hardened. Here you can see in the diagram how these new grains are formed, and in the 7.24 you can see that grain growth by atomic diffusion how it's happening, and here it is given on a as compared to the logarithmic of a grain diameter versus logarithmic of time for grain growth in brass at several temperatures. It is shown. Okay, then this is variation of recrystallization temperature with percentage present cold work for iron. So you can see that in the x-axis or y-axis, x-axis having percent cold work and y-axis having recrystallization temperature. So how it differs. Then in this diagram also you can easily find out that the recrystallization, uh, what is called as recrystallization and how it's happening. And then the figure 26 also changes in microstructure of a strain hardened metal during heating. That is, in the A it is strain hardened metal, in the B beginning of primary recrystallization, in the C end of primary recrystallization, in the D and E stages of grain growth. You can easily see the different stages of grain growth and recrystallization and recovery here in this. So I hope you liked the today's lecture. Going with the MCQs, the decrease in the free energy. Yeah, this diagram is also important from understanding point of view, so you should have a look at that also. Then in MCQ, decrease in free energy during recrystallization is attributed to excess point defects or excess dislocations or grain boundaries or all. The answer is B, excess dislocations. Okay. Then second question, decrease in free energy during recovery is attributed to excessive point defects, excess dislocations, or grain boundaries, or all. You can go with the excess point defects. Okay, because there is a decrease in free energy, only recovery. And higher the degree of deformation, recrystallization is lower. Higher the degree of deformation, recrystallization temperature is lower. Okay, then recrystallization rate varies in the following manner with temperature. That is, it is exponentially. Okay, here you need to understand. Which of the following is not improved by cold working of metals? Which unit cannot be improved? The corrosion resistance will not be improved. Which of the following is not true for cold working of metals? Either residual stresses or stress required to cause deformation. The answer is stress required to cause deformation is less than the hot working of metals. Reduction of cold resistance of metal is wrong in this. The answer is stress required to cause deformation is less than the hot working of metals. Now, in addition to slip, plastic deformation in some metallic materials can occur by deformation of mechanical twins. In this, atoms are located in mirror image positions of atoms on the other side. A simple twinning. Then strong ductile material out of all these metals. Then the figure out the odd statement about ceramics. That is odd statement is ductile in nature. Then odd statement. They are not ductile. Okay. Which of the following deformation occur due to dislocations? Then there is a slip plastic deformation that is happening. Okay. So here are some references which you should look and study for better understanding. And I hope you could like the today's lecture. I tried to cover all the context of recovery, digitalization, and brain growth in this, and obviously tried to explain you the hot working and cold working of materials and tuning effect also. So the motive behind all this is to make you understand the concepts just, and the diagrams that were used to describe all such you can say topics were elaborative enough to make you understand what you have to understand. They will give you a slight idea what if we are studying all about. So for now, thank you very much for attending the lecture, and thank you all.